So we've got the function g here. What I want you to do is pause the video and figure out what g of 1 is, figure out what g of 2 is, g of 3, and g of 4. Figure out what all 4 of these are. All right, now let's work through this together. So g of 1, if n is equal to 1, well then we're going to hit this case right over here. If n is equal to 1, g is equal to 4. So that was pretty straightforward. Now g of 2, if n is equal to 2, well that's 2 is greater than 1 and it's a whole number. And so we would use this case. And this is interesting because it's defined in terms of the function, but it's not defined in terms of g of n, but g of n minus 1. So if n is 2, because we're evaluating g of 2 here, this is going to be g of 2 minus 1, or g of 1 plus 3.2. Plus 3.2. Well, what's that going to be? Well, g of 1 we know is equal to 4. We just figured that out. So 4 plus 3.2, that is 7.2. All right, let's keep going. G of 3. We're going to fall into this case again because 3 is greater than 1 and it's a whole number. So this is going to be g of 3 minus 1, or g of 2 plus 3.2. Plus 3.2. Well, we know what g of 2 is. It's 7.2. We just figured that out. It is 7.2. 7.2 plus 3.2 is going to be equal to 10.4. And then g of 4, well, we fall here again. This is going to be g of 3 plus 3.2. G of 3 plus 3.2. What is that going to be equal to? Well, g of 3 we just figured out is 10.4. 10.4 plus 3.2 is going to be 13.6. And so what you have here, this is actually quite interesting. You can think of this function and this function g, and you see that it's defined over all positive integers. Because it's defined over positive integers, we can think of it as defining a sequence. And we see what the sequence here is. The first term is 4. Second term is 7.2. Next term is 10.4. Next term is 13.6. And it could keep going on and on and on. And what's happening? What's happening in the sequence? Well, we're starting with 4. And that's this case of the function gave us that if n is equal to 4, if n is equal to 1, the function is going to be equal to 4. And then for each term after that, you take the previous term and you add 3.2. So we add 3.2 for the second term. We add 3.2. So we just keep adding 3.2, not 0.32, 3.2 to get to the next term. Now, we could have defined it that way. We could have said, hey, let's have a sequence where the first term is 4, and then we keep adding 3.2 to get each next term. But this is another interesting way of defining it. And this way of defining it, where we defined it as an algebraic function, a function that's defined over all positive integers, where we have a base case. And the base case really in this case gave us our first term. And then we have this other case that's defined in terms of the function that you have to recurse backwards to eventually get to a base case. We call this a recursive function. Recursive function. So with this example, we're seeing how a recursive function can be used to define an actual sequence. And we went in order here, but you could have gone the other way around. If I said, oh well, what's g of 6? Well, you'd go into this case, you would say, okay, that's going to be g of 5 plus 3.2. It's going to be the previous term plus 3.2 if we view it as a sequence. Well, then we're going to have to figure out what the previous term is. G of 5 is going to be g of 4 plus 3.2, and you would keep going back and back and back, but we've already figured out what g of 4 is. It's 13.6, so this is 16.8, and then if g of 5 is 16.8, you add 3.2 there, you would get 20. So you could start at g of 6 and keep backing up all the way until you get to g of 1, and then you figure out what that is. You can recurse back to your base case, and then you're able to fill in all of the blanks. So let's do a few more examples of this. So we have this function here. So let's say that this defines a sequence. Let's think about what the first 4 terms of that sequence are. And once again, I encourage you to pause the video and figure that out. All right, let's work through it. So h of 1 is, well, they very clearly tell us that's going to be 14. If n is equal to 1, h is 14. h of 2, well, now we're falling into this case because 2 is greater than 1 and it's a whole number. So it's going to be 28 over h of 1, over h of 1. Well, we know h of 1 is 14, so it's going to be 28 over 14, which is equal to 2. Now h of 3. h of 3, we're going to fall into this case again. It's going to be 28 divided by h of 2. If we're thinking of this as a sequence, divided by the previous term in the sequence. So 28 divided by h of 2, we know that h of 2 is equal to 2. We just figured that out. So we go back to 14, something very interesting. I think you see where this is going. h of 4 is going to be 28 divided by h of 3. 28 divided by h of 3, which is 28 divided by, this is h of 3 right over here. We just figured that out. Divided by 14, which is back to 2. If we were to think of this as a sequence, we'd say, all right, let's see. The first term is 14, then we get to 2, then we go to 14, then we get to 2. So one way to think about this sequence is that we just keep alternating between 14 and 2's. All of the odd terms of the sequence are 14. All of the even terms of the sequence are 2. That's one way to think about it. Or another way to think about it is we're starting with 14, and each successive term is the previous term divided, is 28 divided by the previous term. So here, 28 divided by 14 is 2. 28 divided by 2 is 14. 28 divided by 14 is 2. And we keep going on and on and on. And that's what was actually going on right over there. Let's do one more of these. And this one is interesting because we now have two base cases. So let's think about this. This is, and actually let's just say we wanted to figure out what f of 4 is. F of 4. Well, we're going to fall into this case. 4 is greater than 2 and it's a whole number. It's going to be f of 4 minus 2. So it's going to be f of 2 plus f of 4 minus 1 plus f of 3. So f of 4 is going to be the sum of the preceding two numbers. All right, so let's figure out what f of 3 is going to be. F of 3, we fall into this case again. It's going to be f of 3 minus 2 is f of 1 plus f of 3 minus 1 plus f of 2, the sum of the preceding two numbers. So let's figure out what f of 2 is going to be. Well, now we're not doing the sum of the preceding two numbers anymore. We fall into this base case. N is now equal to 2. It's going to be equal to negative 4. And we're going to have to figure out what f of 1 is as well. And we see when n is equal to 1, f is equal to negative 6. We have two base cases right over here. Base cases. Cases that aren't defined in terms of the function itself. And you need that because otherwise you'd just be recursing forever. You would never get to actual numbers. But now we can use these to fill in the values up here. So the sequence is negative 6. And then we go to negative 4 as the second term. And then the third term is the sum of the previous two. Negative 6 plus negative 4 is negative 10. Negative 6 plus negative 4 is negative 10. And then the fourth term is the sum of the previous two. We see it right over here. The second term, f of 2 plus f of 3. Negative 4 plus negative 10 is negative 14. And we could keep going on and on and on like that. So this right over here is negative 14. So the whole point of this video, you're a little bit familiar with recursive functions now, and also you can see how these can be used to define actual sequences.